Yeah, so today we will start with graphs, and it's actually again really important topic for interviews. We will see the introduction to graphs only right now. I will do some questions and then yeah, we will go ahead. So starting off right now. So what exactly is a graph, right? Uh, so yeah, like right now you can see there are two types of graphs. Basically, it's just a collection of nodes which is connected in this way. So I can say that this is basically a node. Let me just let me just mark everything for you. So this will be like in this tree. Just consider this left one. This will be called as node, right? This is a one node, and these things are the edges. Let me also mark this, right? So this thing, this is this is H. This is called as H. Just hold on. Control Z. So this is H, right? H of a graph. Fine. We will see. This is now. There are two types of graphs basically, like what we will cover. One, this like you can see two types of graphs, right? So one is the undirected graph. I will explain you what is the meaning of both of them, and this is the directed graph. And if you are like, if you can observe, you can maybe make out the difference right now that basically these have arrows. This type of graph has arrows, and this has just a normal edge, right? So we'll see what all this means. So you can say that basically nodes. You can see that there are nodes in both of them, right? And uh, basically these have, like, if you consider this, this has how many nodes? This has five nodes, right? So five nodes. Fine, this has five nodes, and in this graph, uh, basically now we will see, like, even in the directed graphs, this is a node, like this is a node, and these are the edges. It's called edges only, but it is a direct edge, right? So here this edge is called as directed. Sorry, not directed, undirected. So this edge is called as undirect edge because it's not directing, right? It's not directed to any other node, right? So it is called as undirected edge. This is an undirected edge. However, this is a directed edge. Fine. I mean, like, let's say that we feed some numbers here, right? 1, 2, 3, 4 and 5, right? We feed some numbers. This is also 1, 2, 3 and 4 and 5, right? So here in this case, you can say that like when we are traversing, basically it's like a binary tree only, right? Even if you remember binary trees, it's like basically in binary tree what was happening? It was in this structure, right? It's just graphs is a kind of binary tree only, or binary tree is a graph, not the vice versa. Binary tree is kind of a graph only. It just has some rule that you only, two nodes can be like this and should go in a uni in this way only, right? So basically the here you can see that when we are traversing a graph basically in an undirected way, you can go with one. Basically you can go with 1, 2, 3, 4, 5. What I'm saying here is that if you start your journey from here, you can go to 2, you can go to 3, 4, 5, or else 3 can also go to 5 and 4. If you want to go from 1 to 4, let's say, right? So you can go with 1, 2, 3, 4. You can, okay, let me just draw two ways, right? So 1, 2, 3, 4. Basically, this is fine. This is fine, right? And if you want to go, you can also, if you want to reach from 1 to 5, 4, you can reach also like this, like 1, 2, 3, 5 and 4. So this way is also like possible. So 1, 2, 3, 5 and 4. This is also right. Right, because this does not have any restrictions. However, in this case, you can see the arrows have some meaning, right? Like 1, 2 can move here, right? But after 2 you can't go anywhere because this does not have any, extended arrow, right? So you can go with 1, 5, then you can go to 3, and then you can go to 4. So there, in this case, if you try to move to, if you try to move like this, like 1, 2, uh, 3, and 4, this won't work because the arrows are not directed in a way, right? However, if you go in the arrow, like how the arrow is suggested, so if you go to 1, 5, 2, not 2, 3, right? My bad. 3, then 4. So this can be done. This can be done in a directed graph, right? Because the arrows says so. Got it? So this is the difference basically. Y- Right, like it is more of, specified, right? Also, you can make one more note of this point that binary tree is also represented as a graph, basically, right? Like as I explained here, right? Uh, See, like this is a binary tree, right? This is a binary tree. So binary tree is also, I mean, BT. Basically, BT can also be represented as a graph. Just make a note of this so that you can, like basically why I'm pointing this so that you guys can relate to the concepts that we discussed in our binary tree. It's kind of similar. Traversals are also like kind of similar, but yeah, you will go ahead. We'll go ahead with this. So now, next term which we should discuss is the cycles. Cycles in graphs. Yeah, cycles and graphs. Let's discuss this term, right? So, what are cycles in a graph? Basic, Basically, if you can easily make out the difference. I mean, the meaning of the cycles. Like in this graph, in this directed graph, this was a cycle, right? This is a cycle. So, you can define a cycle. Like if you uh, start from a node, right, and end at a node, at that node, right, then it forms uh, a cycle. Okay, I did one mistake. This is not a cycle. Basically, 153. This arrow, if it was like this, then it would have been formed a cycle. So if the arrow is like this, then you can say that the arrow, like basically, you have a cycle. Uh, you have a cycle in a graph. Excuse me. Yeah, and also like there are two other types of cycles in this case. So there are two types of cycles basically. One is the directed cyclic graph, right? Directed cyclic graph, DCG, and one is the DAG, directed acyclic graph. You can see that if the arrow is like this, and it forms a perfect, cycle, right? Like if you start from here and then meet here, so it is a DCG, right? Directed cyclic, it's directed cyclic. But if the arrows are in this way, like it is not exactly, meeting, then it is a acyclic graph, DAG, basically we call that. We will be using this term a lot, hence I have just, explained it right here, right? Now comes one more term, which is paths, basically. Yeah, what exactly is a path? If we are talking in the context of graphs, right? So basically, this can contain, I will just write, can contain a lot of nodes slash vertices, right? And each of them are reachable. What exactly does this mean? We'll discuss. Basically, yeah, like how here, what I did wrote here, like 1 2 3, this is a path basically. I'm just defining in what ways we can reach to that, right? So let me just show you with one example. So let's say we have this graph, right? It's a simple graph. And what is path in this? Like basically what like starting from here, let's say we start from 1, so I can go from here. It is undirected graph, right? So I can move like this or this or this or this, right? There's no direction, it's directionless. So I can go from 1 to 2, then 3, and then 4. Yeah, so that is one path like this. If you can see the highlights, like this is a path, right? Let me also write that path. So one path, like path uh, like this path 1, one path can be from 1, 2, 3, and 4. And the second path, which is possible, can be like this, right? It's undirected graph. So I can go from 1, 2, and then 5. This is also possible, right? 1, 2, 3, 5. That's also possible. So I can write another path 1, 2, 3, 5. Right. But like you can't go basically this considers, but let me if I consider this path, let's say like 1 2 3 1 2 3, right? And then you again move to 2 and then 1, like in this way, right? 1 2 3 and then again you move this way. So this is not possible. I mean, this is not correct. Right, so these are valid paths, but this is not a valid path, right? Why? Because you can't go back to the visited node exactly, right? So make a note here, you can't go back to visited node, basically, in this case, right? In this case, basically, you can't go back, right? You can start from anywhere. I mean, you can go from to basically like this undirected graph, right? So don't confuse, guys. You can go like if it was directed graphs, right? So if the arrow was only here, then you had to move from here only, right? 3, 4 was the only possible case, but it's undirected. So you can go from here. You can either take this path or take this path, but you can't go back to that visited path, right? Like here in this is happening, right? So that's the thing. Node can't appear twice in a path. You can also write this thing, right? Hence, this hence node node can't appear twice in a path. You can conclude this basically from this point, right? So next thing which we will discuss are degrees in a graph, right? So this session would be like just a introduction only, right? So degrees in a graph, right? So yeah, we will discuss this. So degrees in a graph basically. So what exactly this means is that how many like degree of a node, basically we account for degree of a node. So it just means that how many like degree of a node means how many other nodes it is connected it is connected to, right? That's the easiest definition which I can give, and it's pretty much uh, like it makes sense basically, right? So let's say that let's say that we need to basically find degree of 1, right? So degree of 1 first node, what would be the degree of node? It is connected to 2 and 5, right? So 2, so 2 will be the degree of the nodes. Let's say the degree of 5, right? Again it is connected to 1 and 4 and 3, right? So 1, 2 and 3, hence the degree of 5 will be 3. Got it? Now degree of, let's say, 4. So 4 is this and this, only two connections, so 2. So this is how we calculate basically the degrees, right? And one good formula that you can take a note of this, right? Let me just write that as well. I will, yeah. So please make a note of it. It's important. You can use this in questions, that total degree total degree of a graph is is basically equal. It is equal to what? It is equal to, let me write it little nicely for you guys. Twice, it is of number of edges basically. So this is the main formula, right? So this is the thing. Total degree of a graph is twice the number of edges. Let's say the what is the total number of basically total degree of this graph, right? So one, the degree of one is what, two. So let's add that. Two plus two is two, right? So two plus three of three is one, two, three. So three plus, right? And then 5 also 3, right? Then 4, which is 2, right? So 2 threes are 6, 3 6, which is 12, right? So 12. So total degree of graph, this graph is 12. And how many edges are here? One, like one, 2, 3, 4, 5, 6, 6. So yeah, you can hence prove that 12, 6 into 2. So this proved, right? In this example. So this is a really important formula for you all. So please make a note of it. Now one more thing which we need to discuss, which is like directed graphs are kind of two types of basically terms are there, which is in degree and out degree. In degree means number of incoming edges, and out degree means number of outgoing edges, right? So let's say that we have this graph, right? So in degree of 3, right? So in degree of 3, how many edges are like incoming edges? How many edges are incoming to 3, right? Like how many edges are incoming to 3? There are only one, only 5. From 5 only it is coming, right? So the end degree of 3 node would be 1 only, right? 1. And out degree of 3, basically out degree, how many edges are going outside the 3, right? So like this and this, it is pointing to 4 and 2. So out degree of 3 would be 2, right? So this is how basically very easy, very easy. This is the basics. In degree and out degree refers to, right? So one last term is the edge weight. Basically, the concept of edge weight. Weight. It basically means that in the graph, like also with the edge, number of edge or anything, the weights will be given like 1, 2, like it can be anything like 2, 1, 3, 4, 1 and 5, right? So basically, I mean, these types of questions we will also do. It's kind of like shortest path, but cost, it should cost you basically. Let's say assume that this one is one destination, one city, and 4 is some destination city. These numbers, these weights can be represented as the amount of petrol consumed, right? So like if like question can come, right? If you want to go from 1 to 4, choose a path which costs you like the least amount of which consumes least amount of petrol basically, right? So you can basically compare all the paths, maybe add the all sum of the weights and then compare, or maybe we have more optimized way to do this, right? So we will see all that way. So also one point to note, that assume unit weight of an edge if not mentioned. Basically, if nothing is mentioned, then just assume that the weight of the edge is unit, which is one basically, right? So this just means one, right? So that's all the concepts for the graphs. Now we'll move to the representation part. Now we will see basically how graphs are represented or given in the questions basically, right? So I will just discuss, this will be like how you can see like how you can identify if the graph is being applied in the question or not. That's the whole point of this section, right? So in input basically, let's say you will be given two parameters, right? So one will be let's start with n. Yeah. So one would be n and another would be m, right? So assume that n is the number of nodes, right? And m is the number of edges. That's right. Edges, right? So let's say that this is the graph, right? We have some graph. it's in this way. Like there are uh, these things, and let's say, yeah. So this is the graph. So you can say that n will be 5 because there are 5 nodes, right? And m will be how much? 1, 2, 3, 4, 5, 6. Number of edges. So 6. So let's say that this is the given n is 5, m is 6. You are given these two inputs. So you can just draw this in your rough, right? So like, okay, let me just write one section, right? So like in your, even in the question, you will be given like in basically in lead code or whatever coding platform you use. So it starts from here, right? So input, let's say this is the input. So first will be 5, 6, which means that n, 5 is the n and this is the m, right? Now there will be more things given, right? What will be those things? uh See, so let's say these are the inputs later on. Let me just write and then I will explain. 3, 2, 4, 3, 4, 2, 5, and 4, 5. Right, so these are the some things which is given, just right. So this basically is m lines, right? M lines as in 1, 2, 3, 4, 5, 6. 6 edges. These are the definitions of how the nodes are connected. Like these are the edges given. Right. These are the edges basically. So M lines represents edges basically. Right. So these represents edges. Right. So which means that if it is given 1, 2, right. So this means that 1 is connected to 2. Got it? And same as, so basically it's undirected, right? So 2 1 basically means the same thing, right? Now if it is given 1 3, right? So we can say that some way 1 2 is there, so 3 is also connected with this, right? And same for 3 1, right? Now next is given what? 2 4, right? 2 4, so 1 2, so maybe 4 will be connected some way. Right. So this is how basically the graphs are represented or created, and so on. You can just say that till 4 5 you'll get the full graph, which is right here, right? So so this graph you will get if you are like if you continue to basically just keep forming and forming, you'll get this graph, right? If you keep going it, let me again, like da 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 4 5, if you see that you'll get this graph, right? So this is how basically, like if like input is given in this way in the question, so this is more like identification of how the questions are being formed, right? So now comes like a factor, like how do we store the graph, right? So how do we store graphs, right? So this is a one good topic to discuss basically, right? So which we will discuss. So basically, there are two ways like how we store graphs. One way is the matrix in matrix form, and another is the list form, right? This is often termed as adjacency matrix, right? Let me write that. So this is basically adjacency matrix. So this is majorly termed as adjacency matrix, and this is termed as adjacency list, right? We will learn more about this, but like first starting from adjacency matrix, right? So let's say that we have basically we have some input parameters and the graph, right? So wait, just let me write all this. So let's say that here, this is the input which is given, right? This is the input given. This is the input. So 5, 6, which means that, as I told you, n is equal to 5 and m is equal to 6. And by seeing all these m lines, you can form this graph, right? So this is the graph. Now, like if you want to store this in a matrix, right? What you will do? You will basically create a adjacency matrix. Let's say that you name it ADG, ADJ, and you can create a matrix of n plus 1 and n plus 1 basically, right? So basically if you draw, you will get this matrix, right? You will get this matrix. uh, Let me plot it here, right? Yeah, so you'll get this matrix if you basically plot and all, right? So now starting from 1 comma 2, right? Like after you have plotted this, like the first statement here is what? 1 2, right? It is 1 2. So 1 2 basically, right? What you will do, you will just basically you will treat them as a row and column wise, right? So you'll go to that particular coordinate. So 1 comma 2. You will basically assume that everything here is marked as zeros, right? Everything is zero. So if you have directed 1 and 2, right, after making this matrix, creating this matrix using the n and m value, you will see what is the next thing. Okay, 1 and 2. So you will mark that particular coordinate, right, or that box. So 1 comma 2, how you'll mark it? You will make that 0 as 1, right? So 1 and 2 is done. Basically you are saying that 1 and 2 are basically are they are connected, right? 1 and 2 is done. Now comes what? 1 3, right? So 1 3, where is 1 3? 1 3 is here, right? So make it 1, it's connected now. And same goes for basically as you are doing for 1 2, you will also do for 2 and 1. So you are also doing for that 2 and 1 and 3 1, right? It is getting parallelly checked. So 2 4, now comes 2 4. So 2 4, where it is 2 4, and same for 4 2. 4 2 is here, done. 3 4, 3 4, where it is 3 4. Let me just quickly do everything. 3 4, done. And 4 3 also. 4 3 also done, right? Now what is left? 3 5, 3 and 5 here, 5 and 3 here, done. 4 and 5, 4 and 5 is here, and 5 and 4 is here, done. Everything is done. So these are all marked. So in this matrix form, we have just, uh, we have stored the whole graph in this way. So we can check if there's edge between any kind of a node using this matrix, right? I can write that. So we can check if there is any edge between node using this matrix, right? Why? Because right, like you can, like, these are the nodes, right? And every like it is connected, so everything is 0 0 0 here, right? So if one exists between any kind of node, then it means that there's an edge, right? But like as I told you, this is a one way, right? So even like creating this whole matrix, it's as like it's obvious that it creates a high space, right? Like space complexity is very high. So space basically will be very high. How much it will be? So space it will take like n cross n, because we are creating n matrix, right? N, where n is the number of the nodes, right? So n, which is very high. This is very high, right? Hence, hence you'll switch to another method. This is actually really high. It takes high space complexity, right? High space complexity. So we can shift to list. Hence, we will check how you can store the graph in a list now, right? So before that, I will also write the code for the matrix one, just for your understanding, that what we exactly did, right? So I will just write the code here also. You'll get the whole point, right? So yeah, code I will just quickly write everything, every code here. So let's say that you got int nm, right? I'm just writing a rough code. So yeah, so that it's generic for every language, right? So int nm, if you got the nm, so you can create an adjacency matrix of what size? N plus 1 and n plus 1 basically, right? So you will create the size. Now for int I is equal to 0, I will be less than m because m is the edges, right? So this, right? Now you will have two things, u and v, basically the h, the thing, right? Uh, the edges that you are getting from the next para. So you will input these values, right? U and V. You'll get this U and V, and then you will make in the identity matrix. You'll make that U particular coordinate as 1. Got it? Also, as I told you that even inverse you will make that, because if and this case would be only for the undirected graphs, right? So please to make a note on of that. This case would be for only undirected graphs. So this is how you will basically store, right? So only for undirected graphs. Got it? For directed graphs, I think it's pretty obvious. You won't be doing this. You will just use this first method, right? So yeah, for only for undirected graphs this is the case, right? So this is how we will store. But since it takes a very high complexity, now we'll check out how this can be stored in a list, right? So now here again similar cases given, like input is in given in this way, 5 6 1 2. Yeah, you know that, right? Now we have to see how you can store this in a form of list, which is also called as adjacency list, right? So let's say have this, right? So we can form some relations, right? Let's start from 0. Okay, I'll just write 0. How whatever the number of nodes, just write it here. Like, let me just write them: 1, 2, 3, 4, 5, and 6. Right? Oh, 6 doesn't exist. Sorry. Yeah. So like starting from 0, 0 node is not there, right? So yeah, you can just ignore it. So 1. How many basically what are the neighbors? Basically we are basically creating here the neighbors, adjacent neighbors. We want to create adjacency list, right? So basically we are just finding out the neighbors of the nodes, right? So 0, there's nothing, so no. So for one node, what are the neighbors for this, right? What are the neighbors for this? So it is 2, right? Yeah, it is 2 and what? 3, right? And as you are doing this, so you will also cover for 2. Like as you are storing for like 1, you can also cover for 1. So 2 is also 1, and 3 you can also say that 1 is there. Like this all thing will be, simultaneously, right? Because you're creating a neighbors, right? So because this is undirected graphs, right? So if 1 is the neighbor of 2, 2 is also a neighbor of 1, right? So that's the logic, simple logic. So 1 is done. 1 is done. Now coming for 2. 2, 2's neighbor is 1. Done. Okay. Also it is 4, right? So as it is coming 4, so also write here 2, right? And what else? 5 is also a neighbor, right? 5. So also in this thing, in the fifth one, write 2, right? So this is done. 2 is done, right? Now coming to 3. 3 is 1, that's already there, and also 4. And as you have written for 4, write here 3. Got it? Yeah. 3 is done. Cool. 3 is done. Now coming for 4. 4 is 3. Yeah. 2 and 5 also. And also write for 5. Right. That's done. Uh, 1 4, yeah, that's done. And 5 is 2 and 4, which is already done, because you are correspondingly you are storing it, right? So yeah, that's done. Basically this is how you will store and how you will make the array. Basically I can also write that here only. Let's say that you will make a vector. If you are doing in C++, you can make an adjacent vector of size n plus 1, right? You will make n plus 1, right? And then you will check basically what are the neighbors. And yeah, so as I told you, right, the total number of edges is twice the total number of degree of the whole graph, which is n plus 1, uh, which is total number of degrees, basically what? Twice of the number of edges, right? So in that way, like degree, we can say that the time complexity, the space complexity, it will take twice of the edges of the graph, and this will be, universal for every graph if it is getting stored in the list form array, right? So we will be using, hence, like, since it has very less space, takes very less space, and which makes it more optimized than the matrix way, hence we'll be using this one, right? So since it uses less space, we will be using list instead of matrices, right? Also, it makes sense, right? Because in the matrix, you already saw that you are making a 2D array there, right? And here, but just by using 1D array, you are storing everything, right? You are storing every neighbor and all, right? So now comes the coding part as well. I will also write the code here, right? Let me write the code, write the generic way. I'll write the code as well. Yeah. So here we are given what? Int n and m. Now, assume that this is given. Now you will form a vector int having, which is named as adj, adjacent, having the size as n plus 1. N plus 1 will be the size of it, right? Now for int I is equal to 0, I is less than m, right? Just remember that we are traversing by the edges, given the edges, right? So let's say again here we have int u and v because we want to make edges, right? You can just simply, in the adjacent, you can just push that u. How? Let's see. You can just push back the particular v here, and same but in reverse for v, as I was explaining. Push back u, right? And yeah, done. Just return 0. Done. This is the case. What did I do here? Very easy. I just created an adjacent array, right? Adjacent array, and just was pushing back the u and v. U and v are the edges here, u and v, and they are, as the basically as the input is getting u v, it's getting pushed back to all the adjacent lists, right? So this is how we will be storing graphs in form of list. Got it? Quite easy. And since we are just basically since this has less time complexity, space complexity, we will be using a list for that, right? Also, one more thing: if the graph is weighted, right? So what we can do, like, in if you want to store a weighted graph in form of list, right? So you need to consider the weights as well, right? So let's say that you have you have 4 here, right? So how you will store the edges corresponding to 4 node? Easy, like 2, you can say, you can also make a list inside it, a list basically, right? So 3 4, let's say this is some kind of thing. You can say that, this, the first element is the node, basically the node which it corresponds to. Basically this is the case here, right? 4 2, and this is the weight, so basically this is the case here. Got it? If you want to represent this in a way, in this way, you can store a list inside a list corresponding, and yeah, you'll get the required weighted graph in form of list. Got it? So yeah, that's the note I wanted to give you. Now, as we are moving ahead, one concept you need to be aware of: connected components, basically, right? Connected components. So let's say that you have this graph, right? This is some kind of a graph which we also saw earlier. So this is well connected. So this is a connected component, right? Uh, and this, what about this? This is also connected component. I mean, this is connected component. This can be also called as connected components, right? So there are three connected components basically, right? You can see that. Uh, so that's one concept I wanted to tell you again. Let's say that we are given this case, right? There's one question. One question is given, right? Where n is 10, right? N is 10, and m is what, 8, right? And this is the case. Let's say that this is the case. These are the inputs, right? This is the m lines which is given. So how many connected components are there? There are four connected components, right? Four connected components, right? Four different connected components. Now you need to basically visit every node here, right? How you will visit it? Like you can basically go from one to, right? You can basically traverse this graph some way, but how you will go to this graph, right? Like how will you will keep a check that this is visited, so I won't go, like if you're gone here, you're gone here, gone here, and gone here, right? And since we know, like if you want to create a path, a node should not be repeated, right? A node should not be repeated in a path. That's the rule, right? So how you will keep a track, if you want to go here, how you will keep a track that third, fourth is already visited, so I can't go back to fourth, right? I have to go to 5, 6 unvisited nodes. We will use something called as a visited array. So my point is basically this. For traversing to every node without repeating a node in a path, we can use a visited array, but just to basically keep a track of which nodes are have been visited basically. Right. So easy, like easy way to visualize. So let's say that you have this visited array, right? You have this visited array. Let's say we have it, the name is vis, right? And this is some 0 1 2 basically till how much, till 9, right? Because there are 10 nodes, right? So n is equal to, okay, you need to form n plus 1 array, right? Visitor array should also be n plus 1 size, right? So this should be 10, right? So what you will do basically, like let's say that you have, when you are traversing from 1, you will keep this as 1, 2 traverse 2, 3, you will be like 3, 4, and then so on, right? And then since you can always check if the that particular node is visited or not. How you will write this code basically? It's really easy. Like you can just have for I which is traversed to like 1 to 10, right? You can have this for loop. If you can have this condition, if it is not in vis array, if the I is not visited yet, then traverse the I. Basically, just traverse the I, else just return, right? So yeah, that's the whole point of it. This is the just visited array concept, right? So now we will learn two traversal techniques, basically, right? So it's kind of very similar with the binary tree which we did. So yeah, these are the two traversal techniques. It's kind of really similar with the tree concept. So breadth first search and depth first search. We will be learning breadth first search in this video. Depth first search, I will I have explained depth first search concept in graphs only in one of my reels. Like I also run like my main content basically is in my Instagram channel where I make reels, right? So this you'll get the link in the description, right? But for now, if you are able to explain learn the BFS technique, then DFS you can easily understand by just watching that reel. I explained that beautifully there as well, right? So you can just watch that. But for now, let's jump to breadth first search. So, in to understand VFS, just visualize this graph in this way, in kind of breadths, right? So, here, like n is given as 8. Uh, so breadth you can just basically uh, correlate it with level wise, right? In even in binary tree video, if you have seen the previous video of binary tree, or I guess it's like the second last video, so you can there also level wise or level order traversal was done, right? So breadth and level wise are kinda same, right? Let assume that assume starting start node is 1 basically. Let's say that we are starting from 1, right? We are starting from 1. So how will be this BFS traversal will be, right? Let's learn that. I mean, just let's just see the what is the BFS traversal. How will be the we will traverse? So it will be in level wise, right? It will be in level wise. So basically, starting from 0, it will traverse every node at the next level, and then it will go from next level, and then so on, right? So let's say that it starts from 1, so 1, right? That's done. Now it will go to 2. It can either go to 2 or 6. Basically it has to complete the level 1, right? So 1, this level is done. Now coming to 1, so 2 and 6, so you can go from 2 and 6 because you need to complete the level 1. This is done, right? Now jumping to level 2, how many nodes are there? 3, 4, 7, 8, right? So just write that only. 3, 4, 7, and 8. This level is done. Second level is done. Now come to third level. So it's just 5 basically. Got this? It's that's easy. You just need to complete the levels because it happens in level. So this is level 0, 2, 6 is level 1, right? And 3, 4, 6, 7 is what level uh this is level 2, and this will be level 3. So that's how BFS traversal works basically, right? If the starting and the starting node can be anything, right? Let's say that the starting node was 6, right? The starting node has 6. Okay, let's take that example as well. All right. So if start is at 6, right? Then what will be the BFS? BFS. What will be the BFS? Okay. Now coming to 6, we have here 6, this is starting from 6, so it will complete all the like it. Okay, first let me write 6. Now it will complete every basically it will complete everything at corresponding to its it can go to either here or here, right? Like it's in the middle, right? So it will complete all the levels, all the neighboring neighbor levels, right? So we can either choose one. What are the neighbors basically? 1, 7, and 8, right? 1, 7, and 8. So just write 1, 7, and 8. Basically, it just completed all the all the connected neighboring nodes which are at the next level, right? So 0, 1, 7, 8. Now coming to let's say we are here basically we are at 7, right? Or let's say that we are at 1, right? Let's say that we are at, because 6 is done, right? So let's say we are at 1, right? We are at 1. So what are the neighboring of this? Only 2, right? 2, 6 is done, right? So only 2. You can just write 2. Just write 2. Now you are at 2. You are at 2. What are the neighboring of this? 3 and 4, right? So just write 3 and 4. Sorry. So 1 is done. Right. So 7 comes. So now like as 1 is done, so you write of 2. So you have to go in this way, right? Because like we will be using FIFO Q for that, right? So if when 1 is done, we got 2. Now coming to 7, right? We will consider 7. So 7, who's the neighbor of 7? 5. So hence it will be 5 right here. Right, 5 will be done. So 7 is done. Now considering for 8, right? 8. Where is 8? 8 has nothing, so we don't write anything. Now it is done. Now coming to 2. What is the neighboring of 2? 3 and 4. Right, 3 and 4. So we will just write 3 and 4. That's how the traversal of will be done if the starting node is different, right? So here 0 and this will be 1 and this 2 5 will be 2 and this will be 3. So this is how the traversal of BFS would be in all these cases. Got it? So we will be also now we'll see like how you can visualize this in a queue format, like how I explained this, right? You will see that, right? So now we will see like how you can basically start the BFS traversal. Like let's take this starting a point, right? We will be using this vis array, right? As you know, visited array, and this will be a FIFO queue, right? So currently everything here in this visited array will be 0 because initialized as a 0, right? Now as we are traversing, we will push the 1 right here, right? We will push the 1 here. So we will ask like as it is inside this queue, we will ask the 1 who all are your neighbors, right? And also as this is getting traversed, we will also mark this as 1, right? We'll ask who are all your neighbors, right? So what are the neighbors of 1? So it is 2 and 6, right? It is 2 and 6 basically. So we will be using we will be pushing the 2 and 6 here, right? 2 and 6 will be uh, wait, let me just write it in smaller way. 2 and 6, right? So now 2 and 6 are there. So this is we are considering this. So 2, just mark 2 and 6 also listed array, right? And as we are marking, we will also mark this as 2 and 6 because we have pushed it, right? And since 2 and 6 is there, we will also mark this as 1, and for the 6 we will mark this as 1, right? Yeah. So FIFO, that's done. Now using 2, we will ask the 2 as it's FIFO, first in first out, right? So we'll ask 2 who all are your neighbors, right? The 2 will be like, okay, my neighbors are 3 and 4, right? So will we push 3 and 4 here. So 2 is done. 3 and 4 also will be using this. 3 and 4. So 2's is 3, 3 and 4, and we can also add 2 in the 3 and 4th nodes, right? Now same goes for 6. We'll ask 6 who all are your neighbors. 6 is 7, which is already no 7, which we will be taking, right? 7 and 8, 8, right? So 7 and 8 are visited, right? They are visited. So 6 is done, right? 7 and 8 are visited. Now consider for 3. Okay, I also have to write 7 and 8 here, right? So what was the step? 6. Okay, 7 and 8. And I also need to write for the 7 and 8 and 9 is also there, right? So 6, 6, right? Yeah. Anyways, so that's it. Now checking for 3. Okay, 3, three's there's no neighbor, so just pop that out. Now 4, 4 neighbor is 5, right? So write 5 here and also make it fourth neighbor as 5. So make it 4, 5 and also make it as 4. Basically, we are doing the same thing which we did earlier. Now 7. For 7, you will say what are your neighbors. 5, which is already done. So like see, now considering for 5, we will see that neighbors are 5 and 6. So you'll check the visited array. Oh, 5 and 6 already visited, so you'll just simply pop this out, right? 5 also you can write this 5 7, and 7 also will have 5, right? Same goes for, yeah. Now consider for 8, right? 8 is the neighbor is 6 only, right? So 6 only will be there, which is already visited, so there's no problem with 8. Now checking for 5. Is there any neighbor in 5? In neighbor 5, which is 4 and 7, which are already there, right? So don't there's no 9. So 8 will be only 6, 7 will be 6 and 5, that's right. And this will be basically the case. If I'm missing anything, am I missing anything? No. 4 is 2, 5, 5, 7, 4, 7, 6 is 1, 7, 8. Yeah, that's done. So yeah, as the if the queue gets empty, you will know that the all the traversal has been done. So this is how we will be doing the BFS traversal. Yeah, that this is all the BFS traversal using queue, which is FIFO, right? So now I will be writing code here, just the code here as well, right? So code, it's actually also quite direct and easy, right? So I will be writing code now. So please pay attention to this as well, right? So I will be I will be using a vector int, right? A vector int which will be named as BFS, right? BFS, which will take int v, right? And it will also take a vector of int, which will have some, which will be some adjacency matrix, right? This will be the BFS function, right? Now coming with, we will use a visited array n. Let's take n, right? The size will be n. So yeah, small correction, this will be n size, so there is no 9. Got it? This will be of n size. We'll be using the vector array as name because we don't need n plus 1, right? So what's the use? Now we will make the, we can make the 0th as 1, right? So now we'll be defining a queue structure, right? We can say that this is some queue, right? Some queue, and as we this is the starting node, right? This one is starting node. That's why I'm marking that as 1, as it's been visited, because we are at that, right? So we push 0 as the 0th. We start from 0. We can push that. Now, now this loop starts, right? This will be q dot size. If q dot size is not there, if there's nothing, start keep in the loop. Now we can have this node which will be q dot front. Basically we will take the front of the queue, and then we will also pop this out, q dot pop, q dot pop, we'll pop this out, right? Q dot pop. And we can also, we can just, bfs dot push, we can just push that node in the same function, right? We can just put that, push that node in the same function. And now we can have this thing for auto it, right? Adj of node, agency of node, right? If now we are checking if it is visited or not. If this array has the it, right? If this array has the it, then this I is equal to 1. I mean it's not, then just make that as 1, and also push it in the queue, right? Push it in the queue. I'm just writing whatever I'm just writing it in a queue code form, whatever we did, right? So there's nothing much to basically worry about. And after that, just return whatever is left in the BFS. Got it? That's the whole, just return the the vector, right? Which has all the stored, which has all the path, BFS path, right? So this is a simple code, nothing much. The time complexity, yeah, we can discuss the time complexity as well of this code. It's nothing like the space complexity. The space complexity would be somewhat as O to power 3n, because we are using three sized data structures. One is vector visited array, right? So which corresponds to O of n only, right? And time complexity, what about time complexity? Where it would be O of n plus one traversal is done with the this thing, and then there's one loop, right? Uh, so hence this will be the O2e, because it's the H, right? So yeah, so this is the whole buzz about BFS. Right. Now, if you have understood the BFS, you will understand the DFS as well. Like for DFS, basically, like just note, like for DFS, not BFS, it's DFS. So for DFS, like just link in description and pinned comment as well. Just check out the pinned comment of this video. You'll get the link of the DFS video of the reel which I have created. It's actually really easy. So it's kind of like your homework. Like try out the like just see this video of DFS, which the link will be in description in the pinned comment. You will understand the DFS from there only, right? So yeah, that's all. Now we can have one question. One question I can do. Like we have just discussed every traversal, right? Like please come to this question after seeing the DFS thing, right? So this question is actually really popular, and I just wanted to discuss the approach of it, right? Not the whole question, just the approach, or maybe let's see what we do. Number of island. If you may have heard of this as well, but yeah, let's discuss this, right? So basically. So in this question, basically, you can treat a matrix basically, which is given, right? So it's like a grid or matrix, you can say. So a grid is given here of like a grid is given of size n cross m, right? Where n is the like row and columns, right? So zero, you can say that zero represents water, right? And one represents land. Got it? And grid is given in this way. Right, let's say that grid is given in 0 comma 1, right, 1 comma 0, 1 comma 1. It can be in these ways, right? 1 comma 0 comma 0, 1 comma 0, right, like so on. So this is the thing. Now you need to basically this is the, let's say that this is the given grid. What you need to do is that you need to make islands, right? So let's say that this is a island, right? Like collection of lands is one island. This can be called as one island, right? And this can also be a one island, right? So, oh, sorry, this whole. So, right. So this one, two, three. So the answer you need to return is three. The number of islands in this grid. Right. So, like this, like just seeing at this question, can you say that these can be represented as a graphs? Right. And this is kind of like connected components question. Like the connected component, basically the connected component which we discussed, right? Connected components. We discussed kind of the like this, right? So like, uh, yeah. So what we can do here. So remember in connected components, what did I told you? Right, let's say that this is one, basically this is one component, this is one component, and this is also one component, right? So three components. So basically three points will be there where you will start the traversal, right? So there are the three starting points. Starting points. So can we say that if we have three starting points, basically we can have the three islands, right? Did I made the question really easier? Like, okay, the number of uh, starting points is equal to number of island, right? Because if this is one graph, this is one connected component, and we have one starting point, this means that there's one component, right? If this is some another component which has one starting point, this second component, right? So we can say this rule, right? Easily we can say that the number of starting points is equal to the number of islands. So can't we just find the number of starting points in this? We can, right? We can find, now we need to think how we can find the starting point. So let's apply BFS for, like, if you need to basically search the neighboring ones, right? And it should be in this all the ways. So we can use BFS there, right? So BFS, we can apply BFS here. How? Let's see. So let's say that for now, let's say that the starting node is 0 comma 1, right? 0 comma 1. So this is the starting node basically. This thing is the starting node. Fine. Let's take that, and we can just basically make 2D array, 2D visited array, right? We can make a 2D array of visited ones. So basically what I mean here is that what we can make here, we copy paste this. So we can make a visited 2D array, right? So 2D viz array, right? Yeah, you can make anything, but let's start from this here, right? So I can make a 2D visited array, and I can have one queue, right? I can have one queue here, and also you can also note that let's say that this is one node. So the island can be made if there's exist another node at all 8 directions basically, right? So this is something you need to note basically: 1 2 3 4 5 6 7 8, right? So that this is the whole point of this, right? So basically island can be made if all these directions, if there's exist any kind of node in all the 8 directions, right? Excuse me. Yeah, so starting from 0 comma 1, 0 comma 1, just make it 1. Fine, that's 1. So 0 comma 1, you can just push it here. Now ask if there are any, what are the neighbors of 0 comma 1. It will say okay, there are neighbors, right? So 0 comma 2 is 0 comma 2 is one neighbor, right? 0 comma 2 is one neighbor, and 1 comma 1 is also one neighbor. 1 comma 1 is also neighbor. So you can just pop this out, and now consider for 0 comma 2. 0 comma 2, basically you can make 0 comma 2 and 1 comma 1, right? 0 comma 2, what are the neighbors of 0 comma 2? It's 1 comma 2, right? I mean, I'm just like remembering this thing, right? 0 comma 1, so you can just correlate with that. Yeah, only that. So this is done. Now check for 1 comma 1 and 1 comma 2, right? So 1 comma 1, 1 comma 1, what is the neighbor of 1 comma 1? This thing, 2 comma 2. So just write 2 comma 2, and 1 comma 1 is done, right? Now coming to another next one, which is we write it little bit cleaner. 1 comma 2, 1 comma 2, 1 comma 2 is this, right? So just visit this array, right? And 2 comma 3, this are there any neighbors? Yes, 1 comma 1, which is already visited, right? So 1 2 comma 1, 0 comma 2 already visited, 2 comma 2 already visited, so there's nothing. Now this 2 comma 3 left, 2 comma 3, 2 comma 3, wait, 2 comma 3 should not be there. Have I done some mistake? 1 comma 1, okay, wait, what is the 1 comma 1? It is 1 comma 2, it is 2 comma 2, this should be 2 comma 2, not 2 comma 3, it should be 2 comma 2, 2 comma 2, right? So 2 comma 2 will be there, it's done. So this will also be, left, and as the queue gets empty, you can just conclude that one island is done, right? If the one island is done, right, if the queue is empty, right, you can just have all other starting nodes, you can just conclude. Now you can just run, basically you have, wait, you have considered this and you got one, right? So now you can go to next node, You will say, okay, it's already visited. Okay, fine. Then, okay, let me just explain that. See, you got the starting node here, right? You got the starting node here. Now you will go to, you ran this. If you get the starting node, you will run this thing, this whole stack thing. You'll get, you will basically mark you'll basically mark all these things, right? You'll basically mark all these nodes. Now you'll go to next node. You'll say, oh, this is already visited, so you'll go to this next. You'll say, okay, this is 0, so there's nothing to worry about. Then you will go here, right? 0, okay. 1, you'll go here. Okay, 1 is already marked, so yeah, this island is already counted, right? So you'll go here, already marked, go here. 0, nothing, so go here, go here, go here. 1 already marked, right? So go here, go here. Similarly, when you reach here, you'll be like, okay, 1 is there, but it is not marked yet. So again, you will start this whole stack traversal, right? You will again start this whole traversal, and then you will again mark these two. Basically, you will have one island. You will add the one island, and then you will be like, okay, this is done. Starting point, this is done. Now we'll check for this one. This is already visited because you just did the stack one. You will go here. 0, nothing. Now this not visited yet. Now you will again start a traversal. You will say that, okay, this is only one island, and yeah, that 2 will become 3, and then you will return that answer basically. Right. So this is how you will basically handle it. I will just write some statements here. Right. So let the starting nodes you would get would be like 4 comma 0, right? And then it will just turn to basically 4 comma 1, right? As the traversal is beginning, as the island is getting more and more, and then you will get 4 comma 3, right? That's the whole point. And how to decide the starting point, right? Like traverse, so just traverse from 0 comma 0, yeah, 0 comma 0, and then do BFS, just do BFS, then keep checking, keeping visited vis array, repeat, just repeat this whole thing, right? This is how you will do. And the code will be, I will just give you one gist of the code, not the whole thing, because this I guess you can do right now. So code will be kinda like this. See, like for row which goes from 0 to n, right? You can have one more matrix for call which goes from 0 to m, right? So if if the visited is not visited basically, row call, right, it is not visited, then do BFS on that particular coordinate or that particular node, and just do the count plus plus basically, right? Because as you know, BFS is happening, you are making sure that the island is there, and then just return count. Yeah, that's the whole code. I mean, that's just the gist of the code, what you have to do, right? So you can just use queues and all. So yeah, similar question, which will be our homework. I mean, just you can just I will just write the keyword. The homework words question is on the rotten tomatoes, and even this question I have discussed in my Insta channel basically. This link will be in description. Basically, first try this question. Then if you find difficulties, then you can just go to the my Insta channel. The link will be in the description, and check out how I have done this rotten tomatoes question. Right. So yeah. So keep practicing, and yeah, basically what I did here is that I just explained everything here. Right. Uh, if there's any doubt, uh, basically I just written this code. So the starting node, I will just give one more kind of, revise this brought to this question. So we just made a queue. We had one island. We like basically we just concluded one island after after just checking this 2D visited array, right? And as we are discussing and as we are basically moving this array all, we are concluding if the island is visited or not, right? So this is the small code basically. Like you can start from here, right? And if you found one, basically, if you found one, if it is not visited, then do the BFS at that particular row and column, and then you will get basically whenever you are running a BFS, you are making sure that the island is getting count, right? Right, so hence you'll see and count will be incremented, and then again just go keep going on to this whole matrix, and you will get three starting points basically. Three starting points means three islands. So yeah, that's what we will return. And yeah, so till now this is all we will do. Homework is Rotten Tomatoes question, which I have done in my Insta channel as well. Link will be in description. But first try it out, Rotten Tomatoes question by your own self. And then if you have any doubts, then we will you can just comment in the comment section or in my Telegram channel. Right. So yeah, that's all for today. I will see you in the next video. Okay, cool. Bye.